Hello and good afternoon to everyone present here, and welcome to this webinar titled Modeling and Simulating Electromagnetic Linear Actuators inside SOLIDWORKS. My name is Arvind Krishnan and I will be your presenter today. And on behalf of our company EMWorks, I welcome you all for today's webinar and thank you for taking the time to attend this. Before I start, just a few bookkeeping items. First of all, I would humbly request all the participants to please mute your uh, audio device, sorry, your microphone, so that there is no echo or any disturbance for the other viewers. So thank you for muting your microphone. The next thing is we are going to use the GoToMeeting session today. So if you look into your GoToMeeting console panel, there is a chat section. That's really the third button from the left to right in these top icons. And in the chat section, you are welcome to type in the questions that you would like to ask me during this presentation. And at the end of this session, I will go over these questions and try my best to answer them. So even if you have any questions during the presentation, feel free to please type those in to the chat session. With that, let us go ahead and take a look at the agenda that we have for today. Today, we will be talking about linear actuators. And one can think of two distinct type of linear actuators. There may be many, but today we will talk about two of them that are very popular. The first one is solenoid based actuator, and the next one is a voice coil type actuator. So we will be looking at both these types. We will compare them and contrast them as regards to the advantages one presents over the other. Next, we will use the EMS product to do live simulation of two of these types of actuators. One, the solenoid, other is the voice coil. Then we will go over some EMS product bundles so that you are familiar with what kind of products we offer. And finally, we will recap what we went over in this demonstration. Also, we will be recording this session and a link to this recording will be sent to you. So let us start with the two types of actuators that are commonly used in the industry. We have on one hand the solenoid type of actuator and on the other hand voice coil type of actuator, and the diagrams are given in this slide. So what is the basic difference between the two? In the solenoid type actuator, the coil that actuates, the coil where the current is passed, is usually stable, which means it's non-moving. And the plunger is the movable component. In the voice coil actuator, the coil, again, which carries the current, oftentimes is also the moving component. And in the voice coil actuator, the force acting on a current carrying coil placed in a magnetic field is actually Lorentz force. And it's this Lorentz force that makes the movement of the voice coil in a voice coil actuator possible. In a solenoid actuator, on the other hand, there may be force acting on ferromagnetic components, but because the coil which carries current and which is largely responsible for creating the magnetic field, is stationary, the force acting on the ferromagnetic component is magnetic in nature. And this is predominantly the phenomena that explains the force acting on the magnetic component in a solenoid actuator. In a voice coil actuator, the source of the magnetic field is always a permanent magnet, whereas in a solenoid actuator, there is no requirement to use permanent magnets to generate magnetic field. So as a result, you can see in a voice coil actuator, there will always be a magnetic field, whereas in a solenoid linear actuator, the magnetic field is turned on and off based on whether your coil is excited or not. So these things are the major differences between the two in terms of their operation and in terms of their design structure. Let's take a little closer look at the comparison between the two types and see how they can play a role in the kind of application that you are designing. If you look at the voice coil actuator, they tend to have much longer strokes, and we will presently see why that is so using the graph on the right side. Whereas in a solenoid actuator, their strokes are very small, very limited. The voice coil actuator, because the source of the magnetic field is the permanent magnet and the Lorentz force acting on the coil is directly proportional to the strength of the magnetic field produced by the permanent magnet, there is an inherent limitation as to what kind of forces you can generate using this. Because the magnetic field that you can generate in a voice coil actuator is limited to the size of the permanent magnet that you use. And the other component that generates the force, which is the current, is also usually limited by the type of coil and the number of conductors that you use to wind the coil and the wire gauge of copper used, etc. So the force that you can expect from voice coil actuators, they are lower in magnitude. However, their forces remain more or less within a constant range. Whereas in a solenoid actuator, because you are actuating using a coil which can be subjected to high currents, you can technically generate very high magnetic field, and as a result, you can create a very high force on the moving plunger for a very short duration of time. However, the force is really proportional to the position of the plunger. So if the plunger is far away from the source, which is the coil, then the force tends to be lesser than when the plunger is closer to the coil. So the force, though high, is not constant in a solenoid actuator. Voice coil actuators are fantastic devices because you can actually have movement in both the direction. By changing the direction of the current in the voice coil, the direction of the force changes because the magnitude of and the direction of the magnetic field produced by the permanent magnet remains constant. So voice coil actuators can actually be reversible with respect to their movement. However, in a solenoid actuator, the reversibility of the plunger or the moving component is often accomplished by using springs, mechanical devices like springs, and turning off the excitation of the coil. Because of this reversibility that is easily accomplished in the voice coil actuator, they are used for position or force control. Whereas the solenoid actuators are usually used as valves to open and close certain devices. They're also used as switch gears which can establish contact or break contact. The cost of voice coil actuators is slightly more expensive because of the use of rare earth permanent magnets. Solenoid actuators, which don't need these kind of magnets, tend to be cheaper. On the right side, I have a graph that kind of explains the force versus the stroke of both the voice coil as well as the solenoid actuator. You can see that the voice coil actuator, whose graph is shown in an orange color, tend to have a much larger stroke as we discussed here, and also almost a constant force over a good stroke length. Whereas the solenoid actuator, although starting with a very high force when your plunger is close to the coil, rapidly degenerates as far as its force is concerned as the plunger stroke is increased. So you can see the behavior of these two types of actuators. Both these actuators are very common in the industry, and EMS product can study both these types of actuators, as we will see shortly. Next, we will go live where I'm going to show you the EMS product to simulate first a voice coil actuator, and then we will look at the solenoid actuator. Now here you see a model of a voice coil actuator, and for the simulation that I'm going to be showing you today, we have certain objectives. The first objective is going to be to compute the force on the coil at any given position. And also the next one is to see how this force brings about movement of the coil, and also what is the value of these force as the voice coil moves. And finally, we would like to understand the distribution of magnetic flux in the model. Let me now go to my SolidWorks and then bring about the voice coil actuator model. Here is the model of a voice coil actuator that we will use today to study. Let me take the section view and explain to you the components that are there. What you see highlighted is the permanent magnet whose direction of magnetization is in the Y direction. Surrounding the permanent magnet is the coil, as you see here. Then there is also a ferromagnetic structure that is there usually to complete the magnetic circuit. So this is a simple voice coil, and we will see how EMS can be used to study the motion of the coil and also the forces acting on the coil at various times. EMS is an add-in product to SolidWorks. As a result, when you install EMS, you will be able to do the magnetic simulations right inside SolidWorks. So here is the SolidWorks assembly. Once you design your assembly inside SolidWorks, you can come straight away to EMS to do the magnetic simulation. There are a few things that one need to do while doing a magnetic simulation. The first thing that I will bring to your notice is the concept of the air geometry. To do any magnetic simulation, we need to be able to calculate the movement of the magnetic flux. Obviously, inside all the materials, solid materials present in your model, but the magnetic field is also propagated in the air around the model. To be able to capture that, we need to create what is called as an air geometry. Air geometry is nothing but a SOLIDWORKS component that encloses our model. So let me go ahead and hide the air geometry. Once you do your model, you can go to the EMS Manager tab where one can do the simulation. EMS simulations are organized as studies. To do an EMS study, you have to right click and then say study. EMS has several different study types. For things which have permanent magnets and DC actuated current, as in the case of the voice coil actuator, we can use magnetostatic simulation. These are some of the other solvers that are present in EMS. For a detailed information about all the solvers that EMS has, please visit our website. So for this particular simulation, we are going to use magnetostatic. EMS has the ability to couple the simulation with some multiphysics solvers. EMS namely can couple to thermal, motion and structural solvers. In the voice coil actuator simulation, we can couple EMS to motion to really see the motion of the coil. Once you create a study, EMS creates what is called as a study tree. You can see the properties of the study by clicking on the property. So here we have requested, first of all, we have coupled this EMS study to a SOLIDWORKS motion simulation to do multiphysics simulation. Then the next step involves applying materials to the various components. Applying material in EMS is extremely easy. When I go to the right side, EMS contains a standard material library that has several categories of materials as you see here. These are some of the commonly used material in the field of electrical and mechanical engineering. And these materials have properties in them. For example, if we open the folder containing the steels, so you can see the BH curve of steels, you can see other properties that are being used by the EMS material library. The material library is fully customizable, so users can create their own materials and use them for simulation. In this particular example, we have obviously used air as the material for the air geometry. Coil is made of copper, which is a conductor material, and the core is made of soft iron, and this soft iron core is technically a ferromagnetic material. And finally, the permanent magnet is made of neodymium N42. The direction of the permanent magnet is the next item that we need to do. To do that, you can simply set the coercivity direction. And here we can use Cartesian, cylindrical, spherical directions. We also can use a global SOLIDWORKS coordinate system or a local SOLIDWORKS coordinate system. Here you can see that the direction of magnetization for the permanent magnet is along the global SOLIDWORKS Y direction. You can also actually show a preview by hiding these components. You can actually see the direction of the permanent magnet. So you can see a small vector placed by EMS which can tell you the direction of the permanent magnet. So let me go ahead and add back the other components that we hid to see the direction. Once we have completed the material definition, next we come to the definition of the coil. In this particular example, we apply a current to the coil and we use 0.25 millimeter diameter wire to wind the coil, and we apply a current of 10 amps, and the number of conductors in the cross section is 760. So this is the way by which you can apply current or excitation to a coil in EMS. Once we have both the permanent magnet as well as the excitation of the coil defined, we can now request the program to compute the force acting on the coil. And as I mentioned earlier, this force is called Lorentz force. It is actually the force on a current carrying conductor placed inside a magnetic field. Now we have requested the program to compute the Lorentz force on the coil, and this force is coupled with the force item that was created in SOLIDWORKS motion. So let me just go to the next part of setup, which is the SOLIDWORKS motion. SOLIDWORKS motion is a full motion simulation software, and EMS multiphysics simulation is completely coupled with SOLIDWORKS motion. Now in this particular simulation, it is our objective to study the motion of the coil when it's placed in the magnetic field and when you apply a current to the coil. And so we couple that with SOLIDWORKS motion. We want to study that for about 7 milliseconds to see how far the voice coil is actuated. So we create a motion study for 7 milliseconds, and then we create a force acting on the voice coil, and then we denote the force value as 0. What this really means is this is a placeholder where SOLIDWORKS motion gets the actual force from EMS and then runs the motion simulation. And that's the mapping that goes on in the Lorentz Force dialog box, where we want to transfer the force calculated by EMS to this force 1 that we set up in SOLIDWORKS motion. Now once we are done with this, we completed the setup of the problem. We can now go ahead and take a look at the results. What kind of results are available in EMS? First of all, EMS can give you the response characteristics. For example, EMS can give you the position versus time graph. This is the position of the center of mass of the coil as a function of time. And you can get these values here through this table. You can also export these values to a friendly format like Excel or a text file. Next, it can give you the velocity of the coil. How fast is the coil moving as a function of time? So here the linear velocity of the coil is also computed. Then the most important thing here is the force value. If you see here, the force is predominantly in the y direction, making the coil move up. And EMS can give you an idea of the value of force, and you can see how the value of force changes as a function of time, and those values tend to lie between say 24 and 28 newtons. EMS also calculates a lot of circuit parameters that may be useful in designing the circuit for exciting the voice coil. For example, EMS calculates the resistance of the coil. It also calculates the inductance as well as the flux linkage associated with the coil. Finally, one can compute the back EMF in the coil, and you can study how the back EMF of the coil varies with time. So in this particular voice coil example, you saw how EMS actually computes a lot of response characteristics of the coil as well as the circuit parameters associated with this design. Next, we will go to seeing some physical plots. This is a plot of the magnetic flux density in your model. You can actually go ahead and do what is called as a section clipping to study this magnetic flux density in a section plane. So you can actually go inside your model and you can study how the flux density varies within your model. You can see regions of high magnetic flux density and regions of moderately low magnetic flux density in your model. So these are some of the plots that one can get: the magnetic flux density, the field intensity, etc. So EMS can give you both quantitative values like what we saw, the forces, the response in terms of displacement, velocity, etc. Also qualitative plots, distribution of the magnetic flux density within your model. So this way EMS can help you to study your voice coil actuators. Finally, let me go ahead, because this is a transient simulation coupled with motion, I can go ahead and animate this particular model. Here you can see how the motion of the voice coil happens. Because this is connected with SOLIDWORKS motion, we are actually able to study the movement of the voice coil with time in EMS. So let me go ahead and stop this animation and then close this model so that we can take a look at the next model. So we looked at how EMS can be used to simulate a voice coil linear actuator. Just a recap on the objectives that we saw. It was able to compute the force as a function of its function of time or the function of displacement of the coil. And we were able to see how this force varied as the coil moved. And finally, we saw the distribution of the magnetic flux in the model. Next, we are going to take a look at the simulation of solenoid linear actuator. So we saw the voice coil actuator. Now we will take a look at the solenoid linear actuator. The objectives of this simulation is very similar to the one that we did earlier. Namely, we are interested in computing the forces acting on the plunger of the actuator for a given excitation of the coil. Then we are interested in computing the response of the plunger, namely the displacement, velocity, etc. We want the force as a function of time, and we will look at the magnetic flux distribution in the model. So let me go to SolidWorks. Here is the solenoid actuator. We have a coil, as you see here. We have the ferromagnetic components that make up the magnetic circuit, and we also have a plunger. This is a cross section, a section view, so I can turn in and turn off those section views inside SolidWorks. Now, just like before, we will do a EMS study and couple that with SolidWorks motion. Now, if you look at the study properties, here we did a transient simulation, and we want to couple that with SolidWorks motion. The next step involves defining the materials. As you can see here, the ferromagnetic components I'm highlighting, these are all made up of steel 1020, which is selected from the EMS material database. Next, we have the coil that is made of copper, and all other materials are non-magnetic in nature. Just like before, we also have what is called as the air geometry that helps you to understand the distribution of flux in the places where there is no solid component. Let me go ahead and hide the air geometry. Let us now take a look at the excitation of the coil. In the previous simulation, we looked the coil and we applied a current to the coil. EMS has the ability to do both current as well as voltages. In this particular coil, we will use a 30 gauge wire to wind the coil, and the amount of conductors in the cross section is around 925. And then we will put a voltage driven coil where we will apply a constant voltage of 12 volt to this particular coil. It's a 12 volt DC voltage. And then we are going to ask the program to compute the force acting on the plunger. Now this force, as before, is coupled to SolidWorks motion here, and whatever force is computed by EMS will be transferred to SolidWorks motion, and we will be able to do a multiphysics electromagnetic and motion simulation using this arrangement. As before, here is the motion study. There is one new component here. EMS has the ability to study these solenoid actuators with or without components such as spring. In this particular case, I've used a spring that will actually help the actuator to go back to its original position once the excitation is removed. So you can actually study the response of the plunger under the influence of both the magnetic force as well as the spring force. That's the advantage of coupling EMS to a truly motion simulation such as SolidWorks motion. Now, once the setup has been completed, we can now take a look at the results. Just like the previous example, I took the liberty of solving these prior to this demonstration so that we can go straight into the simulation results. As before, one can look at the quantitative as well as the qualitative results in EMS. For example, like before, here the center of mass of the plunger is plotted as a function of time. You notice that the movement of the mass was in the negative z-axis, and hence you can see these minus signs showing that it is moving down. And you can see the movement is not linear like the voice coil actuator. That tells you that the force variation is very large in a solenoid type actuator. In a voice coil actuator, the force is more or less constant, so it's moving under a constant acceleration, and hence you could see a lot of linearity in the response. It's not the case with solenoid. You can also study the velocity as a function of time. You can see that. And finally, the force acting on the y-axis as a function of time. You can see this is the force acting on the y-axis. So as the plunger is coming down, its force increases, and you can see once it's very close, the force really shoots up. So the force response is not at all linear with the position of the plunger. In addition to the force, as I said earlier, because this is a simulation where we are exciting the coil with a 12-volt DC, you can also compute the current in the coil. So EMS can automatically compute the current, and you can look at the raise time for the current to reach a value of say 0.5 amperes. And you can also get the values out into Excel or text format. In addition to the current, one can study the inductance of the coil, one can study the flux linkage, and one can study the resistance of the coil. All of this can be studied as a function of time or as a function of position, just as we saw in the voice coil example. As before, we can now take a look at some qualitative plots. This is the plot of the magnetic flux density in the model through a section plane along the XY plane. You can see the areas of high and low magnetic flux density very clearly using this plot. One can also do a vector plot of this magnetic flux density. Some people would like to understand these flux lines as vectors, and EMS facilitates such a plot as well. And as before, EMS helps you to do an animation of the movement of the plunger. So let me go ahead and do the frames for the animation. And you can see how the plunger moves as a function of time. So initially the movement of the plunger is low because the force values are low, but once it starts getting some momentum, then the plunger closes more quickly. So you can see the motion of the plunger real time as a function of time. You can also see how the flux builds up because The current is not instantaneous. We saw the plot of the current as a function of time. So under a 12 volt DC, the current takes some time to reach its peak value, and hence the forces and the movement of the plunger also takes time in a solenoid actuator. And EMS is able to correctly predict the response of these solenoid actuator. So let me go ahead and stop this animation, and then we can revert back to our presentation here. Again, to recap, we saw a solenoid linear actuator whose objectives of the simulation were to compute the force and the response of the plunger. We saw the force, etc., as a function of time. We also saw some circuit parameters like inductance, resistance, flux linkage, etc. And finally, we saw the distribution of the magnetic flux, and we were able to animate the motion of the plunger. With this, we come to an end of the live demonstration. Then we will proceed with the further parts in this presentation. Now we saw two different aspects of the magnetic simulation in EMS. We saw a magnetostatic simulation of voice coil, and we also saw a transient magnetic simulation of a solenoid actuator. Both these were coupled with motion, and this is a perfect time to introduce you to the product bundles that we have in EMS. The EMS product is actually divided into two main categories. We have the EMS electric, which was not the topic for today, but electric solvers comprise electrostatic, AC electric, as well as electric conduction. Next, we have the EMS magnetic package, which has the magnetostatic, AC, and transient magnetic solvers. All of these solvers can be coupled to thermal analysis, motion analysis, static, linear static simulation, and also to circuits. And these are available as add-on. And EMS licensing is done either as an activation based license, which is the standard license available with EMS, or for an additional price, we can have EMS floating on your company's network as well. EMWorks also has a high frequency product, which was not the topic of discussion for today, but it helps you to design and simulate antennas, S parameters in passive, microwave, and RF components. The EMS product is capable of doing both 2D as well as 3D simulation. Now let us recap what we saw today. First of all, we saw motion coupled multiphysics simulation in EMS. Simulation of linear actuators like voice coil or solenoid linear actuator involves multiphysics simulation, where you need to couple magnetic simulation to motion, and EMS in conjunction with SOLIDWORKS is able to do these types of simulation. Next, EMS gives you a plethora of outputs, and the main outputs are these circuit parameters. We were able to capture the inductance, the resistance, the flux linkage, and also the back EMF in the simulations that we saw. Both types of linear actuators, voice coil as well as the solenoid type, can be easily handled by EMS software. And finally, the product bundle that you would need to do these kind of linear actuators is going to be EMS magnetic with motion add-on. So you would need EMS magnetic package with coupling to motion. Coupling to motion is an optional add-on, But to do what I showed you, you would need them both. With this, we actually come to the last slide of this presentation. On behalf of EMWorks, I thank you all for your time and thank you for viewing this presentation today and attending this webinar. A recording of this webinar will be sent to your email, so please feel free to share it with your colleagues and friends. And you can get more details about our product in our website emworks.com. Also, there are a lot of YouTube videos available in our YouTube channel, which helps you to understand the various aspects of the EMS products. There are also tutorials and live step-by-step walkthroughs that helps you to understand the EMS workflow. So we encourage you to take a look at them if you have time. And finally, should you have any questions regarding the sales of the product, the contacts are established here. Please note down. Feel free to call us and talk to us so that we can give you more information about the product and see how EMS products can actually suit the needs of your simulation and design needs. So with this, I thank you all for attending today's webinar. If there are any questions pertaining to the topic that we handled today, please feel free to use the chat in the GoToMeeting and I'll answer them. So if there are no further questions, then we would like to end this session right now. So again, thank you all for attending today's webinar. A recording of this webinar will be sent to you and hope to see you in a future webinar. So we will be conducting a series of webinars in the coming weeks. So you will get to hear from us. Please register and attend them. Thank you so much and have a nice day.